guys, welcome back. Today's topic is organic stereoisomers. Stereoisomers are compounds, so let's start with formally defining a stereoisomer and the different types of stereoisomer, um, and then we'll go into some specifics later. But formally defined as a stereoisomer are compounds with the same molecular formula, the same connection of on the same connection order, but have different spatial arrangements. So what do I mean by that? Same 2D structure, different 3D structures, I guess, is what you can basically what it amounts to. Yeah. Same 2D structure, but different 3D structures is more or less what it amounts to. So, spatial arrangement refers to the 3D part. So, geometry diagrams are typically shown to distinguish between stereoisomers. Some are mirror images of each other, which we give that a special name, and others are not. So, one type of stereoisomer are conformational isomers, which are different spatial arrangements of the same molecule that interconvert within the free rotation of a single bond. So, bond rotations cause, say, this particular conformational isomer to form rather than this conformational isomer to form. Whereas configurational isomers are stereoisomers that have permanently different spatial arrangements of their atoms. The easiest type of this is to understand is cis-trans isomerism or EZ isomerism, which are configurational isomers where the isomerism results from the restricted rotational freedom of bonds. This is typically either due to a double bond, but you can also see this in some cycloalkanes or alkanes. So here, for example, you can clearly see both methyl groups are on the same side of the double bond, and here they're on opposite sides of the double bond. This is referred to as the cis form, and this is referred to as the trans form. Cis is a Latin prefix meaning to get on the same side, and trans being on the opposite side, the Latin prefix. Optical isomers are configurational isomers that have different effects on plane polarized light. So, such molecules contain one or more chiral centers, and the definition of something that is chiral is a mirror image which is non-superimposable. So, take for example, your hands are considered chiral because they are mirror images of each other. However, you can't overlay those mirror images on top of each other because your thumb will end up where your pinky is, and your pinky your thumb. But that's sort of what chiral is, and they are mirror images of each other. And enantiomers are the specific name given to chiral molecules, which are molecules who have non-superimposable mirror images. So here is the chiral center. A note here is that this is different from this because you can't overlay the mirror images on top of each other. Diastereomers are stereoisomers that have two or more chiral centers. You're not going to be generally asked questions on these. You just need to know they exist. So, and with respect to the top chiral center, these two examples are mirror images of each other. But if you did it with the bottom, they are also mirror images of each other. So they are diastereomers. Since they're not the same non-superimposable mirror images, they create different non-superimposable mirror images. So here's sort of a flow chart of the different types of isomerism that you will encounter. So isomers are compounds with the same molecular formula, but structures that are somehow different. You can have structural isomers and then stereoisomers, and then from that you can have conformational or configurational, and then from configurational you can have cis-trans or EZ isomerism, same thing, or you can have optical isomerism, which can then be further split up into enantiomers and diastereomers, which are non-superimposable mirror images and then non-superimposable non-mirror images. You'll never generally be asked about this, but you will be asked quite a bit on that. So the first thing we need to talk about, the first and probably the easiest one to understand and both really fully grasp, is cis-trans isomerism. This is cis-butene or Z-butene, and this is trans or E-butene, and you always compare it with respect to some reference plane. So in this case, it would be the double bond. And you can see here that they are these two for the cis configuration. They are again on the same side of the double bond, and for the trans configuration, they are on opposite sides of the double bond. So cis, like I said. However, in more complicated examples, there may be two or more functional groups, two or more groups to consider, and that's where you use the EZ naming system. E is German for Eintgegen or something like that. It's German prefixes, and the way you remember it is E is for enemies, and E is for enemies, and they occupy the and enemies want to be opposite each other. So that's the way I remember it, and then Z is the other one. Alternatively, this kind of looks like a Z, I guess. I don't know, but that's the way I remember it. E for enemies, enemies on opposite sides of the plane. That's the way I remember it. Z is used to denote that the two highest order priority functional groups are on the same side of the plane, and E is the two highest order functional groups on opposite sides. Alright, now how do you determine priority? You use these Kahn-Ingold-Prelog priority rules, or however the fuck you pronounce that. And the way you determine priority is you look at atomic number or the sum of you look at atomic numbers. So the one that has the higher atomic number has higher priority. Pretty straightforward. So bromine and chlorine. So if we consider this side here, bromine and fluorine, bromine is a higher atomic number than fluorine, so it has priority. Chlorine and hydrogen, chlorine is the higher atomic number, so it has the higher priority than H. So with respect to those two highest order functional groups, this is a Z isomer and this is an E isomer, since bromine and chlorine are on the opposite side of the plane, whereas here they're on the same side of the plane, and like we just determined, bromine is higher than F in order, and Cl is higher than H in order. Now, what if you had like a methyl group here, and then a methyl something here? What if you had hydrocarbon chains? All right, then you go and look at the atom that's attached to that and check its order, and if it's the same, you then you go to the next atom, so on and so forth. So here on this side, 12, 12, not high enough order. This is more than 12. Bromine has a higher atomic number than carbon, so this gets the order here. Whereas on this side, they're both carbon, so they both have the same order. All right, now let's look to the atom that it's bonded next to. In this case, it would be an H, which has 1, and chlorine, which is a higher atomic number than H. I think it's 35. 35 is much greater than 1, so therefore this gets priority. This CH2Cl group here, and bromine, and since they're on the same side, this is the Z isomer, and this is the E isomer. No, wait a moment. Yeah, no, this is the E isomer, because again, 12, 1, this has the highest order, 12, 12, same order, but 1 and 12, higher order, so this is the E isomer, and this is the Z isomer. For cycloalkanes, since they have decreased rotational freedom, they can also undergo cis-trans or EZ isomerism. You just do it the same way as we just discussed before. The next thing, is there fucking construction going on? Yeah, I apologize if you guys hear that background noise. They are doing some construction. Oops. Alright. That aside, the next video we want to do, oh my god. The next little subsection here is on optical isomerism, which basically, light has wave properties, and you can, you can have polarized light, which is, basically it only vibrates on one plane, the XY plane, the YZ plane, or the XZ plane. But yeah, so it vibrates only on one plane. And basically, optical isomers can rotate this plane in which light is polarized. So, plane polarized light is light that is only oscillating in one plane of motion, in one direction, and basically, optical isomers can change the direction that light has to rotate at. And an optically active compound will rotate the plane of polarized light of plane polarized light, and optical isomers will have different effects on plane polarized light. They will rotate the plane by the same degree but in opposite directions, more or less. And you can use a polarimeter to measure the effect. You can use a polarimeter to measure how much the plane of the rotation is by. So here you have a experimental setup, light source, polarizer, then the polarized light, and then in this gray tube here you have the sample containing the mixture that you want to analyze, and then here you have a polarizer that you can rotate, and you can measure that angle that you rotated it by. Chiral is an adjective, like we just said, referring to non-superimposable mirror images. Chiral molecules are molecules that have non-superimposable mirror images. A chiral center is where like that mirror image plane comes from, and the way you find them, there's a quick and easy life hack rather than having to go through it in your head. If there are 4 different attachments, it's chiral. There you go. Now that's the chiral center, the thing that has the 4 different attachments. So here, for example, here is a mirror plane. If you flip it and take the mirror image, note that that is not superimposable on each other. Note that how that mirror image is not superimposable on each other, and by 4 different attachments I mean methyl, ethyl, propyl, and hydrogen. Those are 4 different things, and therefore it will always produce a non-superimposable mirror image. And a race-mix mixture is, so yeah, that's sort of how, that's the bit on optical isomers you're expected to know. A race-mix mixture is a mixture of 2 equal quantities of the 2 opposite enantiomers, and then generally enantiomers have identical physical properties and identical chemical properties, if not they're very similar. The only real difference is that they rotate the plane of polarized light by different angles, and sometimes, mainly in biochemistry, they will undergo different reactions just due to the arrangement of the atoms. So most biological molecules are chiral, and most things have a great preference for one of the 2 types of enantiomers, the L enantiomer. They generally prefer left-handed isomers, not the right-handed one. Yeah, that's it. Thank you for watching.